quantum hardware can be not only difficult to set up, but in some cases expensive too, right? So how do we iterate on this link layer design without requiring a full quantum network to develop it? And really, that's what motivated our development of this quantum network digital twin. So we spoke about simulation, and this is now moving the needle towards real emulation of the network. So with the digital twin, we're actually able to emulate what we expect from the photon detectors, right? At the end of the day, all we're getting from that quantum magic, all those complicated beam splitters and polarization basis projections and all of that, at the end of the day, the photons will hit a photon detector, and that will produce a click, essentially a signal. It's a classical signal, right? As soon as it hits the detector, we're in the classical realm. The quantum stuff is over. So we can actually emulate what we expect from those detector clicks at very high rates and in different scenarios. So that's the role that the digital twin essentially plays. And it's feeding our key generation controllers, our link layer devices, so we can actually test out and iterate on this design. It has some really nice properties. It's a purely classical test environment. So there's no fancy, expensive, or really hard to implement kind of quantum hardware here. This is all classical hardware. We can also emulate different scenarios and edge cases, and this is really important, right? So we talked about photon loss as one of the sources of errors in a quantum system, but there are other errors too we have to think about. What happens when our clocks go out of sync? What happens if a message gets lost in between Alice and Bob? What happens if the polarization drifts so much in the fiber that our measurements are not giving us the correlations we want? Right? These are scenarios and kind of edge cases that we have to really think about if we're trying to deploy this in a commercial setting and not in a research lab or kind of university setting. So how do we actually test out those edge cases? With the digital twin is really nice because if we wanted to test them out in a real quantum network, we might actually break some quantum hardware, or it might be very hard to actually try and emulate that edge case or that failure scenario that you want to make sure your link layer covers. And finally, there's this nice path from simulation to emulation, right? We spoke about these simulated models that are really at the edge of what theory tells us. And we can trust our simulations. But we can also feed those simulations into this emulated environment, feed that into the digital twin. And all the digital twin is doing is essentially playing these pulse files. It's emulating the pulses that we expect from our detectors at Alice and Bob. So these are some really nice kind of features of the digital twin we've developed.